We're continuing our lessons on proportionality, and we're going to look at what type of proportional relationships are created or exist in triangles that are intersected by a parallel line, and that line would be parallel to one side of the triangle. So the triangle proportionality theorem says that if a line is parallel to one side of a triangle and it intersects the other two sides, then it divides the two sides proportionally. And just kind of shorthand, or in our own words, proportional lines cut the sides of a triangle into proportional parts. So we have our parallel lines here, and we know that because we have these red arrows that tells us that they're parallel. The parallel line is going to be the ED. We are looking at triangle ABC. So AC is the side of the triangle that is parallel to the inserted parallel line ED. And since those are parallel, that line ED, and not even if they weren't parallel, ED intersects the side AB at E, and it intersects the side BC at D. So since it intersects the other two sides and the lines are parallel, then we know we can set up a proportional relationship because that parallel line cuts the sides into proportional parts. So we can kind of look at each side individually. So let's look at side AB. Side AB is being cut into the parts AE and EB. And because ED intersects the other side, it cuts the other piece into segments that are proportional to AE and EB. So AE is across from CD, and EB is across from ED. Or, excuse me, EB is across from DB. Just going to fix my C there. And now we can use this idea to solve problems that have variables or have missing measures. The triangle proportionality theorem. Find the missing side lengths indicated. And we can notice that we have parallel lines, that we have a triangle, so that those parallel lines, this parallel line here is parallel to the one side of the triangle, so that means that it slices these sides into proportional parts. And since we know we have proportional parts, we can set up a proportion. So not even knowing what side lengths we're going to use, we know we can set up that framework for proportion. So the side that I just circled has a length of 15, and then this question mark right here, and we can call that X. So 15 and X are one side of the triangle, and that parallel line divides that whole length. Well, on the other side, the whole length is 14, and we have a piece that is 4, so we know that the other piece will be 10 if we use the segment addition postulate. We can put that in. So on the other side of the triangle, we have 10 and 4. And now we can solve proportions using cross multiplication. So using cross multiplication, we know that that's going to be 10x is equal to 15 times 4 is 60. And we can solve x will then be 6. So let's just test that out. What this means is that the value of 6 will make this proportion right here true. So 15 over 6, is that equal to 10 over 4? That's what we're checking. Do those lengths create proportional parts? So we can see that this side length, or this ratio, will reduce to 5 halves if we divide both of 15 by 3. And then this one simplifies to also 5 halves if we divide both of them by 2. So yes, that value of 6 makes the proportion true. In your warm-up, you were asked to find the length of KL and the length of GJ. And we noticed that if we took KL and multiplied it by 2, we would get the length GJ. We also saw in our warm-up, by calculating the slope, that KL was parallel to GJ. Now, the other thing that we didn't calculate, but we could, is that we could find the midpoint of HJ. That midpoint of HJ would actually be L if we use the midpoint theorem, meaning that this piece and this piece are congruent to each other. We could do the same thing on the other side. HG, we could calculate the midpoint, and that midpoint would come out to be K, meaning that these two pieces are congruent. So there's some relationships here that we could use in other situations. And this theorem is that relationship, that the midsegment of a triangle is parallel to one side of the triangle. So KL is parallel to GJ, and the length of the side is 2 times the midsegment, which here, the length of GJ was equal to 2 times the midsegment. So these relationships can be extended to other situations by saying that if we take 2 times the midsegment, in this case our midsegment is KL, if we multiply by 2, then we will get the length of the side of the triangle that it's parallel to. And this right here is that relationship. Now, how does that relate to the topic we've been talking about, which is proportionality? Well, we know that the side is 2 times the midsegment. So the scale factor between the side and the midsegment will be 2 to 1, meaning that the side is twice as big as the midsegment. So there's our proportion giving us that information. And if we were to do cross multiplication, we would get that 2 times the midsegment is equal to the side. So you could definitely use this relationship if you would rather keep using those proportions. So in this picture, you're being told that QR is parallel to YW. And you're also being told that it's the midsegment because Q is halfway between this side length WX and R is halfway between this segment WX. So YX and WX. So Q must be the midsegment as well. So we know that there's that relationship that if I take 2 times the midsegment, I'm going to get the length of the side. So in this case, the midsegment is 2x minus 3, and the side is x plus 9. So take a second and solve for x. We all should be able to do that at this point now. So pause the video and try to do that on your own. So you should have gotten to a point where you end up with as x is equal to 5. So let's just test that to make sure. So if we plug x into 5 for QR, we're going to get, so we're plugging x into this right here. 2 times 5 is 10 minus 3 is 7. And then we're going to plug x into right here. x plus 9 is 14. So is the length of the midsegment, equal to the length of the side? 2 times the midsegment is equal to the length of the side. Yes, so this must be our answer 5. We can also look at proportional parts when we just have parallel lines and transversals. When 3 or more parallel lines intersect transversals, they divide the transversals proportionally. So we have this first transversal, transversal 1, which goes from A through B to C, and transversal 2, which is E through F to G. And those parallel lines, so let's see how many we have. 1, 2, and 3. So we have 3 or more parallel lines. And really, this is just an extension of that idea, because if we extended these transversals, what do we have? We have a triangle. So we end up having parallel lines that are parallel to one side of the triangle. If you kind of think about about this being a triangle right there. So it's a very related to what we've already talked about in this lesson. So we know that it divides the transversals proportionally. So again, that means that we're getting pieces or parts of a line that are going to be proportionate to other parts of a line. So really, you could just take one set of lines, so AB and BC, and that's going to be proportional to the parts on the other line, which will be EF and FG, and those are set in proportion. And if we just take a look at this, the proportion's kind of set up for us. Isn't this right here, that division bar? It's right here. So we can use this idea in this theorem to solve other problems. So we know we have parallel lines. We have 2 transversals. So we know that these pieces must be cut into proportional parts. So 6 over 5, which is on one transversal, is going to be proportional to the other parts on the other transversal, so that's 12 and x minus 1. Then we can use our cross multiplication to solve problems. Remembering that we have to distribute when we do that cross multiplication. I'm running out of room, so I'm just going to move up here. So I have 6x minus 1 is equal to 60. And, oh, I made a mistake, because just like I warned you to do, I warned you to make sure that you distributed. So, and I did not. So 6 has got to go both to the x and to the 6. So 6x minus 6. So there we go. Then we have 6x. We're going to add 6 to both sides, so that's 66. And then x is equal to 11. So let's just check to make sure that that makes this proportion true. For it to make a proportion true, the 2 fractions on either side have to be equal. That's what it means to be a proportion. So we have 6 over 5. So this is just our check. Over 12, and 10, or 11 minus 1 is 10, because we've plugged that x in for 11. So now, are these 2 fractions, or are these 2 ratios equal? That's what it means to be a proportion. So if we divide both the top and the bottom of this one by 2, we're going to get 6 over 5. This right here is an equivalent fraction. And this 6 over 5 is already in simplest terms, so we know we can't simplify it anymore. So 6 over 5, is it proportional? Yes, so we know we've solved the problem correctly.